Hello everyone, welcome to our final lecture in real analysis. This is week 15. We are going to wrap up the course by talking a bit more about integrals, and we're going to finish off with the one, the only, fundamental theorem of calculus. We're going to prove part 1 and state part 2, and without further ado, let's get going. So, we have a function f from a to b that is integrable, okay? If c is between a and b, then the following holds, and we should all know this from Calc 1, and this isn't difficult to prove. It's very similar to some of the proofs we did in the last video, so we're going to omit that here, but we'll give a little picture. So here's our interval, and c is somewhere in the middle. I don't know why the author said c was in the middle, but just to be consistent, let's keep it like that. So here's f, and so the idea is like, okay, if we want to integrate from a to b, so if we want to find this area, that's the same thing as integrating from a to c and adding it to the integral from c to b, which makes sense, right? So that's our first property, and again, the proof's not too bad. It's very, very similar to some of the things we did in the last lecture, though, so we're going to omit that here and just state it as a proposition. Okay, the next really nice property about integrals is that we have linearity. So what do I mean? I mean that if you add two functions and you take the integral, you can break it up into the sum of integrals, and you can pull out scalar multiples. So if we have two functions that are integrable on a to b, then we have the following. For any scalar in the real numbers, when we multiply the function by the scalar, that is also integrable on this interval a to b, and we can pull the scalar out of the integral. And if we have the sum of the two integrable functions, that's also integrable. And I'm not good at saying the word integrable, but anyway. But anyway, as I was saying, if we take the integral of the sum, that's the same thing as taking the sum of the integral, so we can break it up like this. And yeah, that's it. And we're also not going to prove this because the proof is it's very similar to some of the proofs we did in the last lecture. So, we don't want to overdo it and get totally bogged down and bored. But let's go ahead and prove this one, okay? So this is proposition 8.5. This is called... This is also known as the monotonicity of the integral. So if you have two functions, f and g, which are integrable, and if f is less than or equal to g for all x in your domain, then the integral of f is going to be less than or equal to the integral of g. And I think that makes some sort of sense intuitively. We're thinking about areas here. So if this function is always higher than this function, then when you add up all of the areas under the curve, this one should be, or I think I got it backwards. I meant that if this guy's higher, g of x is higher, then the areas under its curve should be, it should be bigger, right? The area should be more than the area under the f of x curve. So let's go ahead and prove this. Alright, so we're assuming that f of x is less than or equal to g of x for all x. So we're going to suppose f of x is less than or equal to g of x. Then just manipulating the inequality with subtraction, we have g of x minus f of x is bigger than or equal to 0. Now, we know that both f and g are integrable. And so by this proposition, when I multiply any integrable function by a scalar, i.e. -1 in this case, that's also going to be integrable. And I can add, like once I know that negative f is integrable, I can add it to an integrable function and it will still be integrable. So this guy is integrable, is what I'm trying to say here. Because this thing is, and negative 1 times this thing is, so the sum of those things are. Okay, so what does that mean? Well, if I have that this guy is bigger than or equal to 0, right, that means that we're staying above or at the x-axis. So I don't know, maybe this is g of x minus f of x, who knows? But the point is, when I look at the integral, when I look at these areas, that area is going to be positive or 0 as well. Okay, so this is going to imply that this guy is also going to be bigger than or equal to 0. Okay, and by the linearity of the integral, we can break this up into a sum. So this is the same thing as a to b, g of x dx. Pull the scalar out. That scalar of negative 1, so this is f of x dx. This is bigger than or equal to 0, and hence g of x dx is going to be bigger than or equal to this guy. Not too bad there. So that completes the proof of that proposition. Okay, let's look at this one. So, you know, if you're going to take more analysis classes, you should remember this one, because I remember using this a lot in my analysis classes. So just maybe it's not a proposition, maybe it's a theorem. So just remember it if you're going to take more classes like this. All right, so we want to go ahead and prove this. We have a function f is integrable on AB, and we want to prove that the absolute value of f is also integrable, and the absolute value of this integral is less than or equal to the integral of the absolute value. Okay, so we want to show this, and we're gonna do it with Theorem 8.1 from the last lecture. So that was, we need to show that there exists, so for every epsilon bigger than 0, there exists a partition so that the upper minus the lower sums get arbitrarily close to each other, less than epsilon. And that's how we're going to proceed here. So, of course, we're going to introduce epsilon. So let epsilon be bigger than 0. Now f is assumed to be integrable, okay? And remember, the only way you can be integrable is if you're bounded, okay? And so since f is integrable, this means that f is bounded. Now, if f is bounded, right, if f is always going to live in between two numbers, so here's f. It's a great picture, I know, that's not even a function, but whatever, how I drew it. But there's f, so it lives between these two numbers, right? And so if I take the absolute value of f, then that's also going to live between two numbers. There's no way this thing can be unbounded if f lives between two numbers. So this is going to imply that absolute value is bounded, and no, that does not immediately imply that it's integrable, but we do need it to be bounded. Right? So we do need it to be bounded first before we show that the partition, that we have a partition that satisfies that inequality in Theorem 8.1. Okay, so now we're going to use the fact that f is integrable with Theorem 8.1. So this was from our last lecture. Since f is integrable, well, that means by Theorem 8.1 there's a partition. There exists a partition. P epsilon. Let's say P epsilon is, you know, this old boring set that we always choose as our partition, such that, well, what does theorem 8.1 say? It says that U of F P epsilon, so the upper sums with this partition, minus the lower sums, are getting small. Okay, so we have that. And now what we're going to do is we're going to suppose that little mi bar is going to be the infimum of our absolute value of f on any subinterval, so that x is in xi minus 1, xi, and we're going to let capital Mi bar be equal to the supremum on any subinterval of absolute value of f of x. So we have the following. Well, we know that absolute value of f is always going to be bigger than or equal to f of x. Could be equal to if there's no negative numbers involved, but we know for sure that it's going to be bigger than or equal to f of x. Okay, so what does this imply? That means that the supremum is always going to be bigger than or equal. This is going to be bigger than or equal to the supremum of f of x. And similarly, the infimum of this absolute value, so the smallest possible value of this function, is also going to be bigger than or equal to the infimum, right? Because this could be negative of f of x. That could be negative. And so what do we have here? Well, by definition of sups and imps, we have that the sup of absolute f is bigger than or equal to, let's see, oh yeah, sorry, I was looking at the wrong line. The inf of absolute f should be always bigger than or equal to the inf of f, right? And similarly for the sup. Okay, and it's easy to show from these inequalities and just breaking it up into cases whether or not the sups and infs are the same, positive, negative, and what have you, that we're always going to have the sup of f minus the inf of f is always going to be bigger than or equal to the sup of absolute f minus the inf of absolute f. Okay? Okay, so now what we're trying to do is we're trying to show that absolute f is integrable. So now we're going to bring in that the upper sum minus the lower sum and show that the difference between those guys is less than epsilon. So let's go ahead and do that. So we have u absolute f partition minus L absolute f partition. Just by definition of what this means, this is going to be equal to sum from I equals 1 to n of mi bar minus mi bar times xi minus 1. And by this inequality right here, this is going to be less than or equal to this guy. Just replacing that with mi minus mi. Right, we're trying to relate the bars to the regular pieces because we know that we know that, this guy, if I replace the bar f, or the absolute f, with f, then we have that that's less than epsilon just by assumption. Okay, so this is xi minus 1. Okay, and so what does this equal? Well, we know what this equals. This is equal to the upper f p epsilon minus lower f p epsilon, and by hypothesis, since f is integrable, and by theorem 8.1, this is less than epsilon. So since this guy is less than epsilon, by theorem 8.1, this gives us that f, absolute f, is integrable. Okay, so now that's the first part of the problem. Now we want to show the inequality. So we want to show this guy, and that's not too bad. All right, so let me go ahead and erase some stuff so that we can show this inequality. So sometimes this is called the triangle inequality for integrals. Kind of looks triangle inequality-esque. But yeah, I told y'all in like the second lecture, the triangle inequality comes up so many times, it's crazy. It's like, I think that should be the fundamental theorem of analysis, really. I mean, it's like a stupid, like, you use it so much, right? Like, I feel like in every homework, maybe not every homework, but in most of the homeworks, you use the triangle inequality. It comes up all the time. Or the reverse triangle inequality. Okay, so for this next part, we're going to notice that just by properties of absolute value, f of x is going to be bigger than or equal to negative apps fx, less than or equal to positive f of x. And therefore, by the previous proposition, 8.5, by the monotonicity of the integral, we can just carry this integral into the inequality. So this becomes negative ab absolute f of x dx less than or equal to ab f of x dx less than or equal to ab absolute f of x dx. Okay, and so again, by absolute values, since this guy is between negative this and positive this, right, we can just think of these as like numbers. This is negative s, this is s. Then it must be that absolute value from a to b, f of x dx, is going to be less than or equal to this guy. And this is just, again, properties of absolute value. Okay, so that was that proposition. Triangle inequality for integrals. Alright, so let's take a look at this definition. It's just what you think it's gonna... I mean, it's... Yeah, you've seen this before. So if our interval is from a to a, and we're integrating a function f, we say that this integral is 0. And if f is integrable, so if f is going from a to b, we're going to define the integral from a to b of f as negative integral from b to a of f. Okay, so that's how we define these things. Okay, and so recall the mean value theorem for derivatives. So what did that say? That said that if we had a continuous function on a closed-bounded interval ab, and the function is differentiable on the open interval from a to b, then there's some c in that open interval so that this guy holds. Okay, and so what that amounted to was just looking at the slope of a secant line between A and B and saying, well, there has to be some point on this curve so that the derivative has, so that the derivative of a point C in that open interval is equal to the slope of that secant line. So blah, 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 we have this thing. Here's A, here's B, and if we look at the slope of the secant line, that is going to be the slope of some tangent line, maybe this guy. This is going to be our f prime of C. Okay, so that was the mean value theorem for derivatives, and we have a similar one for integrals. We're not going to prove it, but we'll just kind of talk about the idea. Here's what it says. It says that if we have a continuous function on a closed bounded interval from A to B, then there's some C in that interval so that this holds true. If we rearrange this formula by just multiplying B minus A on both sides, we get f of C times B minus A is going to be equal to the integral from A to B of f of x dx. And so basically what this theorem is telling us is that there's some C in between A and B, so that when I look at the area of that rectangle, f of C times the width of the rectangle, which is B minus A, so this is literally the area of that rectangle, that's going to equal the area under the curve. So this area of this rectangle should equal the area under this curve. Okay? So that's the mean value theorem for integrals. Now let's talk about this guy, the fundamental theorem of calculus. So we're going to prove part 1, and we're going to state part 2, but we're not going to prove part 2. So here it is in all of its glory. If you have a function f on a to b into r, and it's integrable, and you have a function capital F from a to b into r, and it satisfies capital F prime equals f, so we have that capital F is the antiderivative of f for all x in a, b, then we have the following. The integral from a to b of f of x is just equal to capital F of b minus capital F of a, and here is a nice little picture of the first part of the fundamental theorem of calculus, saying, okay, we have this curve f, and if I look at the area under this curve from a to b, that's going to be the difference of the antiderivatives evaluated at b and a. So f of b minus f of a. So let's go ahead and prove this. Okay, so let's go ahead and prove this. So we're going to start with a partition, as we usually do with these integration proofs. Let's go ahead and start with a partition P. So let P equal x naught through xn. That's it. Be a partition of AB. Now, by hypothesis, our capital F is differentiable, right? Capital F prime is going to equal f of x. Okay, so capital F of x is differentiable, and differentiability implies continuous, right? Not the other way around, but if it's differentiable, it's continuous. And so what this means is that we can apply the derivative mean value theorem here. So let's write all of this out. F is differentiable by hypothesis. By hypothesis. And differentiable implies continuous. And so since it's continuous on AB, it's certainly going to be continuous on any subinterval of AB. So let's write that. Indifferentiable imply, okay, so f is continuous on any subinterval xi minus 1 to xi of AB. Okay, so then we can use the derivative mean value theorem because capital F is continuous and it's differentiable on any subinterval. So by derivative mean value theorem, there's some Ci in each subinterval such that, well, what does the derivative mean value theorem say? It should say that capital F prime of Ci is equal to the difference of f of xi minus f of xi minus 1, etc. I'm going to write it down. So f prime of Ci is equal to f of xi minus f of xi minus 1 over xi minus 1. Okay, and you can already see at this stage, what we're trying to prove is something that involves differences of f's, and we're already seeing differences of f somewhere. So we're on the right track. Okay, so if I isolate that difference, that's going to tell us, if I just multiply both sides by the denominator, that I have f of xi minus f of xi minus 1 is equal to f prime of Ci times xi minus xi minus 1. Now, also in our assumption, if we go back up here, we have that f prime of x is equal to f of x for all x in our interval. So that holds here as well. So this guy is gonna equal little f of Ci, okay, is the point here. So we have this guy, okay, I'm just replacing that here. Okay, and now we'll bring in the infimums and the supremums, because what are we trying to show? We're trying to show that this difference is equal to the integral from a to b. And so how do we define that? In terms of infs and sups of lower and upper sums. So let's go ahead and define our infimum and supremum on this subinterval. Okay, so suppose mi is the infimum on this subinterval, and in a similar way we can say that capital Mi is the supremum on the subinterval. Okay, so by definition of supremum, so like we can bound this thing, right? We can bound this thing because supremum and infimum are going to be f of something, right? We're looking at the height of the function. And so since this guy is the supremum and this guy is the infimum, we can say that this guy is going to be between them, right? We can say that this guy is certainly going to be less than or equal to the supremum, and it's going to be greater than or equal to the infimum. This is just definition of sup and inf. It's just what that means there. Okay, and so what is this going to tell us? Well, if I bring this back to the sums so that I have lower sums and upper sums, I have the following. I have that the sum from I equals 1 to n of the infimum, xi minus 1, so that's my lower sum. this is going to be less than or equal to the sum from I equals 1. Okay, and since mi is smaller than or equal to f of ci, that means that this sum is smaller than or equal to this sum. Right? I'm just replacing fci here in the sum. Not replacing, but I'm like bringing it up to the sum, right? Because everything else is the same. And this, in turn, is going to be smaller than or equal to I equals 1 sup of, now I'm running out of room, I minus xi minus 1. Okay? So what does this middle term equal? Well, this middle term is going to equal the sum of capital F of xi minus 1, right? Just from this equation right here. If I'm taking the sum from I equals 1 to n on both sides, this is going to equal the sum from I equals 1 to n f of xi minus f of xi minus 1. This, of course, by definition, is the upper sum of this particular partition, and this is the lower sum. Okay. And so this thing is going to telescope when we plug in I equals 1 and we add all the way up to I equals n, everything is going to disappear except for f of xn and minus f of x0. Okay, this is similar to some arguments that we've done before. So we're just going to wave our hands for this one and say, okay, we've already seen this telescoping thing. And this guy is going to be f of xn minus f of x naught less than or equal to u of fp. Okay, but this is xn is b and x naught is a. So this becomes f of b minus f of a is going to be between the lower and the upper sums. And so if we, for any partition, right? For any partition, this is true. So in particular, if I look at the supremum and the infimum of all possible partitions, this inequality is still going to hold true. And so, I'm not going to write it out, but I'm going to draw a little arrow here that, well, actually I will write it out. The sup of LFP, since this is true for every such partition, since P was arbitrary, this is going to be true for the sup. And similarly, true for the inf. Okay, but what's this? This is LF. And what's this? This is UF. So we have this guy, and F was assumed to be integrable. So LF equals UF, right? And so since this equals UF, this equals LF, it must be that that F of B minus F of A is going to be equal to both of these. So right, less than or equal to UF, greater than or equal to UF means equal to UF, less than or equal to LF, greater than or equal to LF means equal to LF. So thus, FB minus FA is equal to UF equals LF equals, just by definition, this integral f of x dx. And we're done. We've shown that this guy equals this guy. So that's the first part of the fundamental theorem of calculus. Okay, so this is the second part of the fundamental theorem of calculus, and I'm just going to state it. We're not going to prove it here. But if we have a function little f, an integrable function, we can define capital F as the integral from a to x of f of t. Okay, so we have a little picture here. So little f of t is this curve, and the area under this curve from a to x, where x is in between a and b, is going to be this region that we're calling capital F of x. Then, as a consequence, capital F is continuous, and if little f is continuous, then capital F is differentiable, and the derivative of capital F is equal to f. So we have an antiderivative situation going on here. And as a consequence, we have that the derivative of this integral, right, is equal to capital F prime of x, which is equal to f of x. And as I said, I'm not gonna prove this, but just so we have it on the books. And that's all that I wanted to talk to you guys about with respect to Riemann/Darboux integrals. I hope that you guys enjoyed the course and that you have learned something. Thank you so much for watching, and I might not see you next time, but maybe I'll see you in another course like abstract algebra, linear algebra, something like that. Anyway, thanks a bunch for watching, and happy learning.